Alright, so in this video, I'm going to go over Faraday's chemical history of a candle. It's going to be about an hour and a half lecture, and so that's going to make it about probably a 2 or 3 hour video. Hopefully I'll get enough information on this where, because really all we care about is the very end. We just care about the comparison to respiration, but in an effort to be diligent and thorough, we're going to listen to the whole thing. So we might not do a lot of commentary on the beginning, and we might just like listen to it and let it play until we get to the very end. I found this through Angela Coiler. I hope I said that right. Dr. Angela Coilers. I hope I don't offend her. But her videos are awesome. I highly recommend, especially this video, how to teach yourself physics. I forget where. Oh, this one, the concept of mass, is really good. E naught equals mc squared is pretty cool if you're into that kind of stuff. I forget exactly where she brings this up, but she's the one who got me this link here. Not personally, just from her videos. She doesn't know me. No one knows really I exist. If you look at my follower count, hey, I'm gonna check. 12 subscribers. Awesome. And what is it, like 3 of those are me? Or just alternate accounts that I subscribe to myself from. Maybe even 4. I don't know. But anyways, we're going to go over this because again, we're going to CPES or CSEPs, or yeah. We're going to the Applied Physics Society meeting. Anaheim. Okay. So we're doing this. We're doing all this. I thought we had to do freaking 3 hours of this, but these are just commentaries. Anyway, I'm going to skip all the commentaries except for the last one for sure. I'm just going to skip to the last one. So 2 hours will be, anyways, it'll probably be over faster if we get started. I'm going to read along while the video plays.
I share with you Michael Faraday's great 19th century...
Yeah, that was going to be an echo. All right.
lecture series, The Chemical History of a Candle. Faraday said of a candle, "There's no more open door by which you can enter into the study of science than by considering the physical phenomena of a candle." Even
Okay, while he talks, I'm going to read this introduction. Well, we'll do his introduction, we'll do Faraday's introduction, and then we'll go.
Even now, 150 years after Faraday delivered his lectures, one would be hard-pressed to find an object of study that would equal a candle. Through a careful examination of a burning candle, Faraday reveals the concepts of mass, density, heat conduction, capillary action, and convection currents. He demonstrates the difference between chemical and physical processes. He reveals the properties of hydrogen, oxygen, nitrogen, and carbon dioxide. And, in a stunning final lecture, he uses a candle to explain human respiration. In creating these videos, we used Faraday's original language because his poetic turns of phrase charmed us. We changed his words only when necessary. We updated terminology, especially chemical terms, and we replaced some demonstrations with modern or safer ones. Even with these changes, the lectures can be a challenge for the modern viewer, and so to help today's viewers appreciate the lectures, my co-creators and I have done 3 things. First, we created an alternate version of each lecture that has a commentary track. In the commentary track, my co-creator Don DeCosta and I guide viewers through the lectures, highlighting the concepts underlying Faraday's demonstrations. And second, we added captions to all the videos, including the commentary versions. And third, we wrote a companion book for this video series that is available as a PDF for free. The book contains the complete transcript of each lecture as delivered in the video series. To help you grasp Faraday's key points, it has an essential background section that explains, in modern terms, how a candle works. And each lecture is preceded by a short guide written in contemporary language. These guides mirror the lectures chronologically, so you can follow while watching the lectures. In addition, the book has a detailed teaching guide. Faraday aimed his lectures toward those new to science, especially young people. His lectures remain today an excellent introduction to the scientific method and serve well as an entry point to the chemical sciences. The teaching guide contains a section called The Big Ideas of Chemistry, which uses simple analogies to introduce younger students to the particulate nature of matter. Following this, the guide contains 6 activities and 1 set of demonstrations that teachers can use to help students investigate for themselves the chemical history of a candle. Each activity has a student worksheet followed by a teacher's guide. Teachers can use these guides and student worksheets for free. We give you the complete book free as a PDF. You can download the book at engineerguy.com/Faraday, or you can buy it as an ebook in paperback or hardcover. So, I hope you enjoy the lectures. For me and my co-creators, Don DeCoste and Alex Black, they were a labor of love. I'm Bill Hammack, the Engineer Guy.
Interesting. That's a lot more than I thought. I need to keep track of for real. It's way rough. Let's go to his. Cool. All right. In the second quarter of the 19th century, Michael Faraday revolutionized our understanding of electrical phenomenon. Let me go back up here real quick. Because I'm thinking about this stuff, but I guess I can speak it out loud. Bill Hammack. These look awesome. I want to do this. That's cool, man. All right. I wonder how they do chemistry. Ooh, it's expensive. Read that. Okay. Okay, let's read this. In the second quarter of the 19th century, Michael Faraday revolutionized our understanding of electrical phenomenon. His impact on our world today is tremendous. It led to the lights in our streets and houses, electrical motors that run our appliances, and the electrochemical processes that refine materials used to make the consumer goods we buy. Beyond this body of pioneering research, Faraday left an educational legacy. His great lectures on the chemical history of a candle. History of the lectures. Faraday presented this series of 6 lectures 3 times. Each time he began a few days after Christmas and concluded in the second week of January. For this reason, they are often called the Christmas lectures. Although their content has nothing to do with the holiday, he presented the lectures in December 1848, 1854, and 1860. A ticket to these lectures was highly prized, even for Faraday. "I am sorry," he wrote to a friend, "I cannot supply Mr. Haggetts with a ticket for my lectures." He entitled the lecture "A Course of 6 Lectures Adapted to a Juvenile Auditory on the Chemical History of a Candle." The term juvenile to Faraday meant what he called young adults, aged 15 to 20. In 1860, 1861, the last time he delivered the lectures, 700 people attended. At the lectures, in the audience sat in tiered seating arranged in a semicircle around Faraday. He lectured from a shallow well behind a large table with a semicircular opening cut out so he could reach his demonstrations, each laid out carefully by him before the lecture. One attendee recalls Faraday's silvery hair and earnest face and his irresistible eloquence, which compelled attention. We know the exact words Faraday used because the 1860 lectures were, in their subtle subtitle notes, recorded verbatim by special permission. It is this version that we edited for the edition of these lectures. Purpose of the lectures. Faraday opens his lecture with the hope that he shall. So this is the last lecture. Sorry. That he shall not disappoint by choosing the candle as a topic of investigation rather than any newer topic. Which could not be better even if it were so good. Although the roots of Faraday's lectures lie in 19th century science and so neglect atomic level description and lack atomic level description, the lectures brilliantly introduce viewers to the nature of science, to the scientific method. Even now, over 150 years later, one would be hard-pressed to find an object of study that would equal the candle. Faraday justifies his choice by claiming that there is no more open door by which you can enter into the study of science than by considering the physical phenomenon of a candle. I think that's pretty fair. I forget the book, but there was a book our teacher read to us in the 4th grade about a guy who stared at a candle until he could see the layers of the candle that was different, and then after he was able to see the layers of the candle, he was able to see the patterns of the universe, almost see the future, or see the future. I don't know. His name was Brown, or I forget. 5th grade. It was in the 5th grade. But yeah, part of his training was to stare at a candle and then be able to see the different layers in a candle. And I did it for a while. I don't know. It just makes you think, watching fire and stuff. If you ever sit around a campfire, it's just cool to chill and just kind of watch the fire dance and it's. I think that's a total human, natural thing. It might be in nature. I mean, deer stare at headlights. I don't know. It is different because I'm not staring at a light bulb. So the analogy doesn't go one for one. Let's continue with this because I really want to get through. We got 200 pages. I'd like to get through this before 2 a.m. Lectures bear out his claim. Through the burning of a candle, Faraday introduces listeners to the concepts of mass, density, heat conduction, capillary action, and convection currents. This part is what we're gonna get into. He highlights the difference between chemical and physical processes such as melting, vaporization, incandescence, and all types of combustion. Good. And by trapping the products of the candle, Faraday reveals the nature of gases. He shows especially the properties of hydrogen, oxygen, nitrogen, and carbon dioxide, including their relative masses and the makeup of the atmosphere. He wraps up his lectures with a grand and startling analogy. By understanding the chemical behavior of a candle, he claims the listener can now grasp the basics of respiration, the essential action of humans and other mammals. This part, Faraday's lectures lie in the 19th century science and so neglect atomic level description. He wraps up his lectures with, hang on, I'm going to change my break. Okay. He wraps up his lectures with a grand and startling analogy. By understanding the chemical behavior of a candle, he claims, the listener can now grasp the basics of respiration, an essential action of humans and other mammals. It is probably with this influence that Max Rubner and Wilbur Atwater, I forget his middle name, get their influence for respiration. I mean, it all comes from Lavoisier anyways, but all right. A candle, Faraday notes, takes oxygen from the air, combines it with carbon in the candle wax, and these form carbon dioxide and water. Humans affect this same chemical reaction when they breathe. Oxygen inhaled with air combines with carbon containing food to produce carbon dioxide and water, which are then exhaled. This analogy of the burning candle to human respiration highlights one of Faraday's greatest themes, how a deep understanding of fundamental science unifies the phenomenon in other physical world. I agree. In addition, I sound so pissed off. In addition, Faraday discusses our interrelation with the plant kingdom. While humans take in oxygen and release carbon dioxide, plants take in carbon dioxide and release oxygen. That is, what is disease to one is health to the other. As P.W. Atkins noted, Faraday knew that substances differ in the number of atoms in each element that are present, but he would have little conception of the patterns in which the atoms are linked together to form the molecular structure to a compound. So it's more accurate to say that because he comes from 19th century science, that he has neglected molecular level descriptions. Yeah. Okay, so this is part of the background. Okay, we gotta read all this, and then he gets to read. This is gonna be interesting. I thought that's what the entire point of the lecture was for, was to describe this. Those are good questions. Okay. I'm not going to go over all this. I'm not. How a candle works. Essential background. To deeply appreciate Faraday's astonishing link of the flickering of a candle flame to how a gasp of air enables life, a reader needs to have a clear idea of the chemistry of a burning candle. For the reader eager to tackle the lectures, remember this is written in 2016. Faraday's is written 163 years ago. This was written 8 years ago. So it's very much modern science. For the reader eager to tackle the lecture, we outline below in a single paragraph the basics of a candle's operation. A study of the more detailed events happening when a candle burns will enhance a reader's understanding of the lectures, and so we've expanded on the quick overview with a section entitled A Detailed Look at a Candle. When a candle is first lit, the flame consumes the wick until it reaches a point just above the wax. This heat from the flame melts the wax by radiation through the air and by conduction through the wick. Conduction is by contact. Convection is by air. Only the tip of the wick burns. This liquefied wax climbs the wick to the flame by capillary action, where the molten wax is vaporized. Interesting. Okay. Next, the flame burns that vapor with oxygen supplied by... Oh my god, I can definitely see the analogy then. It's like, then what draws blood into the muscles? Well, it would be the same as the flame drawing the wax through the wick. Oh, it's still wrong, but you can see the external validity. You know what I mean? So external validity. The degree which findings can be applied to other situations, people, settings, and measures. So it's like you can definitely understand how if fire brings wax through the candle wick, then energy in the muscles brings blood through. That's not how it works, but anyways, you can see the analogy. Next, the flame burns the vapor with oxygen supplied by the surrounding air. This reaction releases gases, mainly gaseous carbon dioxide and water vapor, and heat. The heat release melts more wax, which again crawls up the wick and so sustains the candle's flame. A candle then simultaneously carries out two actions. Its flame burns vaporized wax, and it delivers wax to that flame to sustain it. A detailed look at a candle. While the quick overview above highlights the important actions occurring in a candle, it is in the details that we see the complex chemical and physical processes that occur. We detail below the chemical composition of the wax, the function of the wick, the chemical and physical processes in the flame, and the nature of the emissions from the candle. Sometimes you can just read things super fast and not read it. So I gotta kind of slow down a little, because I could read it, but I want to be able to understand it as well as read it. That's better. Wax. Candle wax is the fuel burned by a candle. The wax is a mixture of long-chain hydrocarbons with the formula CnH2n plus 2. So what that formula means, as you can see down here, the number of carbons, for every carbon, there is going to be 2 hydrogen carbons, or not hydrogen carbons. For every carbon, there's going to be 2 hydrogens plus 2 extra on the end after we added that together. So if you have 25 carbons, then times 2, you get 50, plus 2 on the end, you get 52. The typical composition of the various hydrocarbons averages to 25 carbons and 52 hydrogens. Solid candle wax will not burn, nor will molten wax. Only vaporous wax burns. It's between the 3 states of matter. Solid wax doesn't burn. You can't light solid wax on fire. You can't light molten wax on fire. But if you soak string in the wax and allow the wax to heat up and vaporize, then that vapor will burn. The wick has 2 functions. First, the wick conducts heat from the flame to the solid wax. This heat melts the wax. Second, the wick transports the molten wax to the flame. The liquefied wax crawls up the wick via capillary action. The liquid raises almost to the top of the wick, where it is engulfed by flame and vaporized. Only the tip of the wick glows, and it turns black as it burns. Note that the flame consumes the wick at the same rate as the solid wax of the candle is depleted. The flame burns the vaporized wax with oxygen supplied by the surrounding air. See the figure on page 10. This reaction releases gases, mainly gaseous carbon dioxide and water vapor, and heat. The carbon dioxide is formed from carbon in the candle wax and oxygen in the air, and the water forms from hydrogen in the wax and oxygen in the air. The flame has 3 regions where different chemical and physical phenomena occur. Combustion, the chemical reaction that produces carbon dioxide and water, occurs in the blue outer edge of the flame. Here, the vaporized wax burns completely. Complete means converting all the carbon in the wax into carbon dioxide rather than carbon monoxide. The region, which is the hottest part of the flame, is not uniform. Blue is concentrated at the base of the flame and decreases towards the top of the flame, where it is only a thin layer at the flame's edge. Combustion also occurs in the grayish-yellow section of the flame that surrounds the tip of the wick. Here, the flame vaporizes the molten wax. The liquefied wax cools the flame, and so this section of the flame, the liquefied wax cools the flame, and so this is the section of the flame with the lowest temperature. The wax here undergoes incomplete combustion. Incomplete combustion happens when there's not enough oxygen to combine with the carbon. Air, which supplies the oxygen, cannot travel easily into the flame. Because combustion is incomplete, some of the carbon from the wax remain in the flame. This darkens the flame, creating a grayish cast near the wick. These heated solid carbon particles glow. I don't think there should be a comma there. As they rise in the flame, they create a bright yellow region. This brightest part of the flame has a temperature between that of the hot blue region and the cooler grayish yellow region. The glowing of the carbon particles is called incandescence. This phenomenon occurs whenever a solid is heated enough to emit light. This incandescence is a physical change, unlike combustion in other parts of the flame, which is a chemical change. The chemical and physical changes in the flame create its distinctive shape. The flame's heat expands the surrounding air. It's also a chemical change? It's not just, I understand what they're saying with the physical change, but it's also changing the chemical properties of it in the physical change. So, like, is this the division point between physical and chemical changes? Anyways, like, like an analogy between them. Does that make sense? Okay. The flame's heat, the less dense air draws up cooler air from below the candle. These convection currents create a teardrop shape of the flame. They also sweep away the carbon dioxide and water formed. The importance of these convection currents to the candle's operation is dramatically illustrated when a candle burns in zero gravity or in a vacuum chamber. In these environments, the convection currents no longer occur, and so the flame becomes spherical. The oxygen spends more time in the flame, so the combustion is more complete, i.e. the carbon is turned into carbon dioxide and fewer carbon particles exist in the flame. Because there are fewer carbon particles in the flame's interior is blue. The flame burns out because without convection currents, the carbon dioxide remains in the flame and smothers it. That's so cool. A properly burning candle emits little smoke. Any smoke that arises from incomplete combustion in the flame, tiny particles of unburned carbon mixed with gaseous products. This smoke will soot a piece of metal or glass placed in the smoke well above the flame. The amount of black smoke then depends on the ratio of incomplete to complete combustion. A breeze, for example, can increase the amount of incomplete combustion and cause a candle to emit black smoke. In contrast, the smoke is white and heavy when the flame is extinguished. The white smoke is vaporized wax that has formed into droplets of molten wax. If ignited with a match, this stream of wax can relight the wick as demonstrated in Faraday's first lecture. Convection air currents sweep away CO2 and water. That's cool. Oxygen diffuses into the flame. And the heat. I didn't really read that part. I just kind of said it. Convection current. The less dense air draws up cooler air from below the candle. Yeah, the heat expands the surrounding air. There is no law under which any part of the universe is governed which does not come into play and is touched upon in the chemistry of a candle. I would argue against that. In the chemistry of a candle? Of a candle? He wasn't a physiologist, and there wasn't a lot of physiology at the time, so it's okay. We forgive him. He's pretty great. Heat from the flame melts the wax by radiation, and convection capillary action draws the wax to the wick. Molten wax has vaporized. Chemical reactions produce the flame. Heat, solid carbon particles glow, and convection's currents sweep away the products of combustion. The balanced chemical equation for the complete combustion of a candle is represented by carbon 25 carbons attached to 52 hydrogens plus 38 molecules of H2 oxygen connected to itself, with 25 CO2 molecules and 26 water molecules. Notes on the text of the lectures. In editing Faraday's lectures for the modern reader, we occasionally modified the original text. We updated terminology, especially chemical terms, replaced some demonstrations with modern, safer ones, removed some redundant demonstrations. Faraday often demonstrated the same concept to his audiences. Although that repetition worked well in a lecture hall, it seemed unnecessary in a format where one can watch again. We removed from lecture 1 Faraday's long description of 19th century candles and candle making. I appreciate that. Our largest change was to reduce the number of lectures. We condensed Faraday's 6 lectures to 5 by combining Faraday's lectures 3 and 4. We did a demonstration generating hydrogen from philosopher's wool. We replaced this with his voltaic pile, which he describes in length, with a DC power source. voltaic, voltaic. To help the modern reader, each lecture is preceded by a short guide written in contemporary language. These guides mirror the lectures chronologically, so a viewer can follow while watching the lectures. In the guide, all quotes are from Faraday's original lectures. In the endnotes appended to each guide, we note any major changes from the original lectures. Okay. We did it all. All right. Okay. Oh my God, we have to read one more. The guide. It's already been a half an hour. We haven't even started the hour-and-a-half lecture. I don't think we need the guide. I'm not going to go over this guide. Okay, we're going to go into the lectures. We're going to get this done.